Good morning and most welcome to 1537 of the series. We will today look at an article by Nicolas Gisin, and it's the publisher correction from Nature Physics, volume 6, February 2020. Pages 114 to 119. You can find this page at www.nature.com/naturephysics. Mathematical languages shape our understanding of time in physics. Physics is formulated in terms of timeless axiomatic mathematics. A formulation on the basis of intuitionist mathematics built on time-evolving processes would offer a perspective that is closer to our experience of physical reality. In 1922, Albert Einstein, the physicist, met in Paris Henri Bergson, the philosopher. The two giants debated publicly about time, and Einstein concluded with this famous statement: "There is no such thing as the time of the philosopher." Quite hard words. Around the same time, and equally dramatically, mathematicians were debating how to describe the continuum. The famous German mathematician David Hilbert was promoting formalized mathematics, in which every real number with its infinite series of digits is a completed individual object. On the other side, the Dutch mathematician Luytsen Egbertus Jan Brouwer was defending the view that each point on the line should be represented as a never-ending process that develops in time, a view known as intuitionist mathematics. Although Brouwer was backed up by a few well-known figures like Hermann Weyl and Kurt Gödel, Hilbert and his supporters clearly won that second debate. Hence, time was expulsed from mathematics, and mathematical objects came to be seen as existing in some idealized Platonistic world. These two debates had a huge impact on physics. Mathematics is the language of physics, and Platonistic mathematics makes it difficult to talk about time. Hence, the sense of time was also exposed from physics. All events are the ineluctable consequences of some quantum fluctuation that happened at the origin of time, the Big Bang. Accordingly, in today's physics, there is no creative time and no now. This had dramatic consequences, in particular when one remembers that physics is not only about technologies and abstract theories, but also about stories on the workings of nature. Time is an indispensable ingredient in all human narratives. As Yuval Dolev emphasized, to think of an event is to think of something in time. Tense and passage are not removable from how we think and speak of events. Oh, sorry. So it may seem that physics should give up telling stories and concentrate on more and more abstract theories. But is this the only alternative? Physics is likely to be in danger of coming to a halt when faced with claims like time is an illusion, just as François Rabelais stated that science without consciousness is only ruin of the soul. The mathematical language that physicists use makes it easy or difficult formulate some concepts, like the passage of time. The same holds for our notion of continuum. In reference, I argue that a finite volume of space can't contain more than a finite amount of information, and concluded that physically relevant numbers can't contain infinite information. I've since discovered, thanks to Carl Posey, that intuitionist mathematics comes surprisingly close to my, and I bet many physicists' intuition about the continuum. In this comment, I would like to share my excitement about this finding and argue that the debates between Einstein and Bergson and Hilbert and Brewer ought to be revisited. Bergson never agreed with Einstein's statement, and Einstein's himself felt uncomfortable with the beloved physics lacking the concept of now. Although admittedly he didn't see any way to incorporate it. He thus concluded that one has to live with this state of affairs. Hilbert also felt uncomfortable by the infinities that his beloved axiomatized mathematics introduced, firmly stating that physics should never incorporate actual finities. In order to illustrate the tension physics faces, let us consider classical mechanics. This is a very understood field with known limiting cases: relativity and quantum theory. One may argue that quantum theory is more fundamental and is intrinsically indeterministic. However, the interpretation of quantum theory is still heavily debated, and classical physics, with its enormous explanatory power, is often presented as the idea of a physical description of nature. Hence, for the following discussion, we will consider only classical physics. Although classical mechanics is usually illustrated in terms of clocks and other cogwheels, almost all classical dynamical systems are of a very different nature. They are chaotic, my comment here, or non-linear. Because of the hypersensitivity to initial conditions, the future of typical classical systems depends on far down the series of digits of the initial conditions. A simple but relevant example of a typical classical dynamical systems can be modeled as follows. Assume the state space reduces to the unit interval and consider discrete time steps. The state x is thus described by a number formed by an infinity of digits b that follow 0. At each time step going from t to t plus 1, the digits are shifted by 1 place to the left, with the first digit dropping out. After a number of time steps, the most relevant digit is be n, the nth digit of the initial condition. This digit could, for example, represent today's weather. Imagine 0 for pouring rain and 9 for bright sun, as we have today. If one assumes all digits of the initial condition faithfully represent physical reality, then according to our simple model, the weather of the entire future is already fully determined. This illustrates the absence of any creative time. Nothing really happens, as everything is determined by the initial condition and the deterministic evolution equations. At least this is the consequence of representing the points on the line between 0 and 1 by classical Platonistic mathematics. But is such a representation truly faithful and necessary? My experience is that most physicists reject the faithfulness of such representation, but admit, often with regret, that they don't see how one could do otherwise. For example, Max Born, one of the fathers of quantum theory, stressed that statements like a quantity x has a completely definite value, expressed by real numbers and represented by a point in the mathematical continuum, seem to me to have no physical meaning. This is where intuitionistic mathematics can help. In intuitionist mathematics, numbers are processes that develop in time at each moment of time. There's only finite information. One way to understand this unusual claim goes as follows. Assume nature has the power to produce random numbers. One may think of a quantum random number generator. That would do, but here it is preferable not to think of a human-made randomness source, but rather as a power in nature. Nature is intrinsically and fundamentally indeterministic. Now this source of randomness feeds the digits of typical real numbers, as illustrated in box 1 to the left of the text. Let me emphasize that the digits of all typical real numbers are truly random as the outcomes of quantum measurements, as been nicely emphasized, for instance, by Gregory Chatin. Moreover, typical real numbers contain infinite information. This makes it possible, for example, to code in a single number that answers to all questions one may formulate in any human language, as noticed by Émile Borel. So we have to choose a perspective. Either all digits of the initial conditions are assumed to be determined from the first moment, leading to timeless physics, or these digits are initially truly indeterminate, and physics includes events that truly happen as time passes. It should be repeated. We are put into a choice here between Charybdis and Scylla. Both seem awful at start, at least. But we will notice that one is most definitely more natural for the thinking person. I like this reasoning, it's stepwise. notice that in both perspectives, chaotic systems would exhibit randomness. In the first case, from the point of view of classical Platonistic mathematics, all randomness is encoded in the initial conditions. In the second case, randomness happens as time passes. So you can hear it's a rather distinct difference. As described by the intuitionist mathematics, where the dependence on time is essential, one may object that intuitionism doesn't derive indeterminism, but, very important, but assumes it from the start. That is correct. Likewise, classical mathematics assumes actual infinite information from the start. These two views cannot be distinguished empirically. One can always claim that instead of God playing dice every time a random outcome happens, God played all the dice at once before the Big Bang and encoded all the results in the universe's initial conditions. Despite the empirical equivalence, they present us with very different pictures of the world. Somehow the real numbers are the hidden variables of classical mechanics. But intuitionism goes way beyond the description of the continuum. Physicists often have the intuition that the present is thick. That is, the present is not of measure zero. This corresponds naturally to the intuitionist concept of the viscous continuum. The continuum cannot be sharply cut in two. When trying to cut it, something sticks to the knife. This aspect of intuitionist mathematics is closely related to the law of the excluded middle, which does not hold in intuitionistic logic, Very important. In intuitionist logic, a proposition P could be neither true nor false. This is very difficult to swallow for today's scientists who have been educated within the remit of classical mathematics. But think of a proposition about the future, for example. It will be raining in exactly 1 year time from now at Piccadilly Circus. If one believes in determinism, then this proposition is either true or false, though it might be impossible in practice to know which alternative holds. But if one believes that the future is open, then it is not predetermined that it will rain. Hence, the proposition is not true, and it is not predetermined that it will not rain. Thus, the proposition is also not false. There are similar examples using choice sequences as alpha n box 1. Assume that random numbers are not digits but binary. This goes on until by chance the last n through 2 consecutive tasks R take the same value, after which the series terminates and all future alphas remain constant. Since each time step, the probability that the series terminates decreases exponentially, there is a finite probability that alpha n oscillates forever between below and above half. Accordingly, as long as the series did not terminate, the proposition alpha is less than half is neither true nor false. Hence, the continuum is viscous. It cannot be sharply cut in two, above and below half. In these two examples, the law of the excluded middle holds only if one assumes a look from the end of time, that is, a God's eye view. But at finite times, intuitionism states that the law of the excluded middle is not necessary, that time truly passes and the future is open. Looking at the law of the excluded middle in this way makes its absence in intuitionist mathematics easily acceptable and makes the present naturally thick. Let me emphasize that classical formal mathematics and real numbers are marvelous tools that should not be abandoned. However, their practical use should not blind the physicist. After all, their use does not force us to believe that real numbers are really real. In other words, one should not confuse the epistemological usefulness of classical mathematics with the ontology, which might well be better described by intuitionist mathematics. Furthermore, in practice, one never uses real numbers with all their infinitely many digits. Think, for example, of computer simulations that necessarily at each time only consider finite information numbers. Scientists working on weather and physics explicitly use finite truncated numbers and stochastic reminders. All those who speak more than one language know that some concepts are easier to express in one language than in another. I believe the same is true of the language of physics. Which mathematics we adopt when talking physics will influence the possibility of indeterminism in physics. I believe that the notion of a deterministic and timeless world does not arise from the huge empirical success of physics, but from considering Platonistic mathematics as the only language for physics. Physics can be as successful if built on intuitionistic mathematics, even if this breaks its marriage to determinism. Contrary to usual expectations, I bet that the next physical theory will not be even more abstract than quantum field theory, but might well be closer to human experience. Why, thank you very much, Nicolas Gisin of the University of Geneva, Switzerland. Very interesting. And especially the ending notes here. The problem with physics as being deterministic is not coming from physics itself, but from Platonistic mathematics. And when that is considered to be the only language for physics. And in another important take here that we also learn from the discussions with Stefan Mangold, all classical systems are nonlinear. We know that for a fact since chaos theory. So we know that reality does not really parallel easily with the deterministic worldview, since even the systems that people often proclaim are typical for classical mechanics, like building houses, bridges, roads, trains, are inherently non-linear, and that at the end it's stochastic principles that makes it possible for us to do those things, not the underlying gestalt or foundational theory that the world is deterministic. Another important take is that there is no empirical way of showing whether the naturalistic intuitionist is more closer to the truth or if it is determinism. But you can see why determinism developed if you understand that we grew up. Our civilization was founded on Platonistic views. It's an inheritance. And that inheritance, of course, makes the choices. One can see David Hilbert as being infused with these ideas of the law of the excluded middle, and that even a very small point could contain an infinite amount of numbers, which I feel is absolutely nonsensical. Sorry, David Hilbert. All of intuitionist mathematics in physics makes a lot more sense. Not a little more sense, but a lot more. And since time disappears because we happen to more or less by default choosing the Platonistic worldview, there was a quite significant price to be paid for choosing this path and not the other one. I'm going to put a pause now and can see what time it is. So, welcome to the summary of the interesting article by Nicolas Gisin of Geneva University. As you can see here, it seems that we are under the influence of, say, outside the scope of mathematicians. We are under the influence of unknown ruling principles. And the choice of mathematics changes all of reality. You will have no time and you will have no space. This is close to what I showed in 1529 with a light semaphore. In this sense, everything is determined by the initial conditions, or time changes spontaneously and things do not remain the same. What is the most important difference here? I'm going to put it here. I'd say the most important difference here is that in one of the examples we become ruled by deterministic viewpoint, makes all choices nonsensical, because God threw the dice by the Big Bang, and after that all was decided. And we were left completely choiceless. Or God is continually throwing dice, and time really has the character of being different, changing. A true flow of time. And it's interesting that the viewpoint for determinism was decided already in this maybe terminating for philosophy meeting between Henri Bergson and Albert Einstein in 1922. Where he concluded with his famous statement, "There is no such things as the time of the philosopher," thereby nullifying philosophy for 100 years, making it mute, a eunuch, forceless. When I studied philosophy, and also when I studied mathematics, Platonistic mathematics was always assumed from the very outstart. It was the default mood. No other options were really viable or possible. And since the Platonistic take is empirically provable, there was no real reason other than to accept it. It worked, so why not stick with it? Nicolas Gisin admits that both the intuitionist take and the Platonistic take are empirically, verificationally equivalent. But choosing one over the other makes an incredible change. If we have the intuitionist, the days of Henri Bergson are saved. There's still a very good reason to think that time is real and that there is a now, and that time changes everything. Compare that to the Platonist view, and in reality we are still assuming that there is a randomness, only that the randomness is at the very outset of the universe. That seemed to be the only difference. They both yield the same result, but they have significant philosophical and human value consequences. We end up with a science that is not intelligible. As there's a quote from François Rabelais, "Science without consciousness is only ruin of the soul." And how many physicists, mathematicians, biologists do not claim that time is an illusion? So you see, the consequences are quite grave. It has implications on all facets of human life, excluding nothing, including everything. And I would say I will go one step further and take the line of the physicist Lee Smolin and the Brazilian philosopher Roberto Unger. It makes harm to the thinking capacity to assume these things. It is not reasonable to think that everything is determined from the outset. It's a claim that comes from unawaring accepting Platonistic realism, a traditional viewpoint that we inherited. And yes, it is in our blood. I would say it's even in our language. We are infused with it. But we need to question it to preserve and reclaim our thinking capacities, because accepting Platonistic realism makes us dumbfounded, makes us less thinking, feeling, understanding. Therein lies the problem. So it's much graver and greater than only physics. It goes beyond and into the everyday life, because time is all. So we have to choose a perspective, a quote from page 115. Fourth paragraph on the right column. So we have to choose a perspective. Either all digits of the initial conditions are assumed to be determined from the first moment, leading to timeless physics, or these digits are initially truly indeterminate, and physics includes events that truly happen as time passes. And I say that sounds much closer to real time. It speaks to common sense, or speaks, I would say, to our thinking capacity, much more than unwittingly assume that God threw a dice at the very start of the world, because we inherited Platonic realism from antiquity, and we cannot question it because we are so infused with it. We are used to it, I would say. But I am very sure we can question it, because the more you ponder about these things, the less sense do they make. Of course, it needs to be discovered first. Since these things have been sort of nested within thinking and knowledge for a very, very long time. And it's almost impossible at the outset to even see that they are there. The law of the excluded middle often gets so customary, like a habit that is impossible to quit. It's like scratching your head or urging for a sip of water when you're not really thirsty, or walking in a specific way. All those are decideful and deciding habits that make things work in a most specific way that is almost unavoidable. And we naturally give into it. There is no questioning about that. But when giving into it, of course, we lose our freedom. The gestalt, the attitude of thinking that everything is determined from the outset and all happenings are ruled by that primal igniter, that first mover that settles everything. And then we are stranded with the panopticon, of course, and we get the homunculus, we get this weird outsidedness of reality. We get so many thinking paradoxes that we have to give into. And I think those, for every time we accept such a thing, we make thinking less. It becomes minor. It will not have the same substance. And it lessens our capabilities. Take, for instance, the cosmological fallacy. If we accept that that is a reasonable thing to think, we question the foundations of thinking itself, that it is coming from us. We put thinking outside of ourselves, outside our time and space. We make it less deciding. We accept the passivity it gives, and therefore we become less thinking in every aspect, whatever we do. Because thinking is outside of us is disastrous. We lose the grip on the horse that is our thinking system. We lose the possibility to steer our thoughts, to be masters of them, and we lose the ability to rule our own fate, our inclination. We lose the incentive to direct ourselves, and we naturally collapses. We naturally collapse. There is a very important physical side. And once the intellect is not in ourselves anymore, connected to our beings, we already have the Cartesian dualism well established. So Nicolas Gisin's article is pertinent on a lot of things that we already sort of looked into in various ways. It is of incredible importance to get this message out in some format, to make it understandable for the common man. So he does not think everything is determined from the very outset. That there is still a human will, that we can make choices that makes a difference. It's not hard to see whether which one you choose, or I would say even that you do a choice, because Platonistic realism is not a choice, I would say. It's already there, it's the default. This is what we get when we don't choose because we are unaware. That's why I think this article is so important, and several others I noticed by Nicolas Gisin, to point to this incredibly important divider in human existence, that between having a choice, being the ruler of your own world, and the other one having no choice at all, being governed by something you don't even know about, that you simply because of tradition assume. That is true slavery. It's not hard to see that that assumption will sort of make all your doings in your life, all your wants, understandings, realizations less. You will be ruled by what you do not know, most definitely. I will continue with a little more information from the magazine Quanta. I'll put a short pause here.